My name's Ben, and today we're going to be talking about linked lists. Linked lists are a common data structure in programming. In this episode, we're going to be talking about singly linked lists. So from now on, when I say linked list, I truly mean a singly linked list. Linked lists are different than arrays and ArrayLists. Arrays and ArrayLists actually are a contiguous piece of memory, where a linked list has nodes, and these nodes are scattered around the memory space in the system. The way we navigate through a linked list is using these things called nodes. A node is kind of like an element, but it's really another class that wraps an element. And in this node, we can keep track of the next node in the linked list. So that's how we can traverse through a linked list. Because a linked list is a list, it has to support the following functions: add, insert, delete or remove, contains, size, get, and set. Before we move any further, we have to get some definitions down. We have to define two different classes here: node and linked list. A node is a class that we can define with a value and a reference to the next node. Therefore, a linked list is made up of nodes. The linked list will be the class that implements the list interface. The way we will define this is a linked list will have an attribute called head, and that head is a node. It's the first node in the linked list. So adding to a linked list really means that we have to create a new node. And it is implied when we add to a linked list that we're actually adding to the end of the linked list. Let's talk about the case where the linked list is empty. If the linked list is empty, well, all we have to do is create a new node and set that linked list head to that newly created node. That's it. Now consider the case where the linked list is not empty. What we have to do is we have to go into that linked list and we have to iterate or traverse all the way through that list, get to the end, find the last node, create a new node, and set that last node's next reference to that new node that we just created. What does that mean? Well, we just had to traverse the entirety of the linked list to add that new node. That means that our runtime is O of n. But consider if we made our linked list a little bit smarter. What if we created an attribute of the linked list to be having a notion of the last node in the list? Let's call that tail. Let's give our linked list an idea of its tail. So if we need to add to a linked list and we know the tail, what we can do is just do tail.next equals new node. And boom, we've done it. What we've done there is we've actually changed our runtime of how this add works. We have changed this runtime to from O of n to O of 1, a constant runtime. And what we've just done is I've actually surfaced to you a huge portion of programming. It's this concept of trade-offs, and a specific trade-off that we're talking about is found everywhere. Do we compute or do we store the information? And if we compute, that means in this example, if we compute, we must go through the entirety of the list and go to the end, and then we can actually insert our node. We'll always be right, and we don't have to use memory to describe anything, but it is slower. If we decide to store some information, right, we store that tail, we have to use more memory, but we also don't have to do that huge computation to get to the last node. So in certain places, in certain implementations, it may make sense to choose computation over storing. And obviously, there are situations where storing is more preferable. Memory is cheaper than CPU. This depends all on what you're doing. When we're inserting a node, it's very similar to adding a node, but we are given an index to insert at. If we're inserting at 0, we know that this new node that we're creating is going to be the head of the linked list. And what we can do is use that to our advantage. Let's create a new node. Let's put our value in that node. And now what we do is that node's next, we set that node's next to head. Now effectively, we've created an ancestor to the linked list's head. Now what we do is we tell the linked list your head is not the true head anymore. It's actually this newly created node. And what we've done here is now we've basically redefined what head was as the newly inserted node. So if we traverse through the linked list, now our head is that newly inserted node. But if we're not inserting at 0, things become a little more complicated. When we insert at a non-zero index in a linked list, it's a little bit more complicated. And we have to rewire these notions of nexts in some nodes. So what we will do is we'll go into the linked list and we will create a counter. And when we're at head, when we're starting the counter, our counter will be at 0. And what we want to do is we want to create a loop and constantly increment and go through the array. We're going to traverse the array, and as we go through each node, we're going to add 1 to our counter. We're going to stop when our counter is equal to the index that we are inserting at minus 1. We're going to stop at the node right before the node we're going to insert at. We're going to take this node and we're going to call him parent. And parent's child is going to be called old. The first thing we will do, having parent and old, is we're going to create new. New is just the newly created node. And new, we're going to set news next to old. Then what we will do is we will take parent and set parents next to new. So then what we've basically done here is we have broken the association between parent and old, and we have stuck new in the center of them and created the association where parents next is new and news next is old. We've just inserted a node into the linked list. Now, if you think about this, let's also think about its runtime here. If we're creating a node towards the end of the linked list, maybe at the end or just before the end, we have to traverse all the way through every single node until we can do that breaking of association and insertion and rewiring those nodes. This means that we have to go through everything, right? Which yields a O of n runtime. Deletion is a common operation we do on linked lists. And when we do a deletion on a linked list, we have to do some Indiana Jones style of replacements. When we delete a node from a linked list, I am going to assume that we are given an index to delete at. To make things a little bit easier, we cannot delete from an empty list, and we cannot delete at an index that is bigger than or equal to the size of the linked list. When we're deleting a node, what we have to do is, again, we have to traverse all the way through the linked list until we're at the node we're trying to delete's parent. Therefore, we traverse all the way through the linked list until we are at index minus 1, where index is the thing we're trying to delete at. And what we do is we take that parent node, and we obviously have this concept of next pointing to this node we need to delete. So we have this concept of parent, and what we do is we also store the node we're trying to delete's next reference, right? So now we have the parent, and we have this concept of the new next. And what we do is we tell the parent's next reference to equal new next. So we've kind of just gone around that linked list node right there. So we've just kind of just don't include it anymore. And that's how a deletion works. When deleting from a linked list, think about what we just did for the runtime. Well, okay, we have to go all the way through the linked list and until we're at that index that we need to delete from. And then we do that rewiring. We cut out and we rewire around that node. Now consider if we're trying to delete towards the end of the linked list, right? We have to go all the way through and then delete it. There's no way we can get around, and there's not really a way we could utilize the tail there. This means that to delete a node in a linked list must be O of n runtime. When we're doing a set on a linked list, we don't have to do any sort of rewiring of references or orders or anything. It's really simple. When we set a value, we have to traverse through a node, and we traverse through the node until we find the node whose index is the one we are trying to update. And then all we do is we set the node's data to be this new data. But as you saw, or as you just listened to, we have to traverse through every single node until we get to that node. So what happens if we're at the end of the list or the end of the list minus 1? right? We have to go all the way through, and then we can set that node's value. A set on a linked list is O of n runtime. Compared to an array list, when we're doing contains on a linked list, it's really the same operation. We have to go through every node to see if the value we are looking for is present within the list. And so, worst case scenario, the element that we're looking for, the node or the value we're looking for, is at the end of the list, which means we have an O of n runtime. Now, we've talked about trade-offs before, and so as we talk about the size function, we have to talk about trade-offs again. If we are computing size by traversing through the entirety of the linked list, then it's going to be an O of n runtime because we have to go through every single node, right? All the way through memory. But if we somehow give the linked list an idea of what its size is, and we set that size when we do an insertion or a deletion or an add, anytime we truly mutate the size of the array or change the size of the array, we update its size, well, we can store that, and that's an O of 1 runtime, which is a constant runtime and very fast. Now, if we're trying to get a value in a linked list, we usually have an index that we're provided. So as an example, get the value at index equals 2. So what we have to do is we have to travel or traverse through that list until we arrive at the index we are looking for, and then we can return that value. But again, think about it this way. What if the index is towards the end or the last node of the list? If the index is at the last node of the list, then we have to go all the way through, which means our runtime is O of n. So in conclusion, linked lists are really cool in the way they're really flexible. They can handle a lot of different data. They can handle more data than an array list, and they're not subject to that amortized time. That means that the memory could be in different spaces of the system. This means that the operating system may have to go searching for these memory addresses and then start piecing things together. We'll talk more about memory management and operating systems soon, but just know right now, if the difference between the memory addresses for variables or for memory or whatever you're working with is too drastic, that means your operating system will have to go search for them, and then once it has all of those things you're looking for, it can then continue operation. Linked lists also suffer from the fact that gets and sets are an O of n runtime, where with an array list, because it's powered by an array and the memory is contiguous, all we really have to do is just access that array, get the information or set the information there. You know, I'm really starting to enjoy making these YouTube videos, and if you'd like it and subscribe, I'd be really, really appreciative of it. Please show this video to your friends if it's helpful, and feel free to message me in the comments or message me over Facebook or Instagram, or check out our website, pragmaticsoftwareengineering.com. Thanks, guys.